Hello everyone, my name is Carson Haack, a master's student at the University of Alabama and student in the AEM 617 Aircraft Systems class. Today I'm going to be giving a lecture presentation on the investigation of the Swissair Flight 111 disaster featuring aircraft wiring. So, in honor of Failure Friday, even though it might not be Friday, depending on what day you're listening to this lecture, Swissair Flight 111 was also known as the UN Shuttle. It was a flight from New York to Geneva that crashed on September 2nd, 1998, and the main cause of the fire was determined to be an onboard fire that led to failure of electrical systems and loss of aircraft control, resulting in 229 lives lost. On the right-hand side here, you can see that we have the last words of the cockpit pilots and the air traffic control. Now, if you look over at the aircraft, a McDonnell Douglas MD-11 shown here on the right, which, side note, I don't know why KLM thought it was a good idea to paint an aircraft light blue and white when it's going on the sky, but that's another topic for another day. It was entered in service in 1990 as a replacement to the DC-10. DC-10 was a wide-bodied aircraft that was designed to still be a wide-bodied aircraft, but not be as big as a Boeing 747. Its main feature is the tri-jet design here, which the tri-jet design was a feature that came as a result of an FAA policy requiring that aircraft with two engines must be within 60 minutes flying time of an airport. Because if one or two engine fails, the aircraft must be able to divert into an airport, which slang for that rule was engine spin or passengers swim. The MD-11 featured a glass cockpit. I'm not talking about the windows. The glass cockpit means that the displays are digital, which we'll see later, instead of mechanical gauges. And also some new features was the fuselage of the MD-11 is longer than a DC-10, and there's different airfoil design, and they have these little winglets to increase the efficiency. Another thing that is a main improvement over the DC-10 is that there are hydraulic fuses, which the DC-10 did not have. And after American Airlines Flight 191, where the left engine came off and came out over the wing, the electrical systems were destroyed, but hydraulic pressure was also lost, meaning the control surfaces along the leading edge, it collapsed, and the plane rolled and crashed. So the hydraulic fuses are there to maintain hydraulic pressure in these wing areas, or all over the aircraft. So if electrical failure will not lead to a loss in hydraulic pressure. There are still 127 in MD-11s out today, but they're pretty much all used as freighters. The wide body is favorable among cargo companies because you can carry more cargo in the same kind of size airplane without having to use a 747. Here's a schematic of the MD-11. You can see the kind of signature design, 3 engines with a wide body and the winglets. You see I have a front view here, inside section, 342 seating, and the top and side views. Here's the layout of the cabin. Here we have these station numbers which represent distance in inches along the aircraft. Notice that the front nose is at station 239, where some people might say, why isn't it at station 0? Station 0 is almost always in manufacturing somewhere along the front of the aircraft. Well along the front, actually. This is to make sure that if they put some sort of instrument or probe out in the front, that nothing goes past station 0, so that a station measurement will never be a negative number. So they kind of fudge it by having 239 as the main station. The main area of interest is going to be at station 383, which is where the cockpit door is. You can see we have the galley, the entrance doors, and the lavatories. Down at the bottom, we have a fire chart, which lists all the probable areas of fire. These blue areas are areas where there's not really specified on any sort of fire. So we have the main cabins, the attics, the avionics compartment, this drop ceiling area where the fire did end up happening, and the cockpit. The yellow areas are areas where fire could potentially happen, which is the cargo compartments, because cargo is made out of flammable materials such as fabric, luggage, and cotton clothing. And then the orange areas are areas where there would normally be expectations for a fire, which would be engine, which makes sense, and an auxiliary power unit. So an overview of the electrical system. This is an electrical diagram for the MD11. This type of diagram is not like the circuit diagram you'd find in a circuits class with resistors and diodes and inductors and batteries everywhere. This is a block diagram. So it outlines different, switch the laser pointer here. It shows different areas that circuits would be tied to, like these buses and the generators, as well as the batteries. This kind of system you can see is a parallel system, which means that the wires, the circuits aren't in parallel, but these buses are. The buses are giant hubs where other circuits are connected to. So, for example, we have this generator right here, which corresponds to one of the engines, connected to both this generator bus and the main alternating current bus. But these buses, this bus 1 is connected to generator bus 2, which is connected to generator bus 3, which is connected to this tie bus. The tie bus is the parallel bus. So if one of these buses fails, it's still connected to the other ones through the tie bus. We also have our ADG, which we'll learn about later is a turbine that can generate emergency power. We have our emergency buses, both alternating and direct current, and the batteries over here, and these little things right here are switches. So a little glossary about some of the terms. AC is alternating current, DC is direct current. I didn't put that in the slide. Oops. The ADG is the air-driven generator. It's a manually deployable turbine that spins when the aircraft moves, and it generates power, emergency power for these buses and the battery chargers. Which a bus bar, when I say that, is pictured here. It's a big metal bar. Normally copper acts as pretty much a giant all-directional wire that can transfer electricity to other systems or within a switchboard or a circuit breaker board. So these buses all have other power systems or other systems connected to it to deliver power. EXT power, that's some sort of external power source. Probably not going to find one of those in the air. The IDG is the integrated drive generator, or the engines. Each engine, when it spins, turns a generator, which provides power to the rest of the aircraft systems. And the static inverter and these TRs, this static inverter takes DC power and converts to AC power. And on the other hand, the transformer rectifier converts AC power to DC power. So power is able to be transferred between these two halves of the electrical diagram. Now, in emergency mode, this electrical diagram changes a little bit. We have, in emergency power mode, when you only have the battery running, you have the batteries connected to the battery buses and the DC bus and the emergency AC bus, which these are the systems that can be powered by the battery-only mode. They're listed right here, but I decided to blow them up because that's kind of hard to read. The display electronic unit and the display unit. The display unit is the actual display, and the electronic unit is the brains behind the display. We'll see this later in an image of the cockpit, spoiler alert. But these actually display all of the instruments and the gauges that would normally be on a mechanical or analog display. The engine and alert displays power and emergency alerts that is going through the engine. The multifunctional control display unit deals with flight paths and aircraft navigation, which you also have your inertial reference system and your flight management system. The flight management system is the brains behind your multifunctional control display, and this is actually just the display, and this is your inertial navigation, which we learned about in a previous lecture. The VOR and the VHF are omnidirectional range beacons, and VHF stands for very high frequency. In a previous lecture, we learned about navigation by radio, which navigation by radio seems to be a very important thing to have in the event of an electrical failure. And the PFD is your primary flight display. The primary flight display is displayed on one of these display units, and it features an artificial horizon, a heading, an altimeter, and an airspeed indicator. In electric mode, when you have the ADG being powered, it's powering this ADG bus, which transfers power to both of the emergency AC buses, which is also connected to the emergency DC buses, and the battery bus. It's also connected to a battery charger, which can charge the batteries. And in addition to all of these systems up here, it can also transfer electricity to the flight management system and high frequency radio, as also the instrument landing system. The flight management system, it takes flight plans and puts it out into the multi-function control display unit. And the instrument landing system helps the pilot land automatically without doing it himself. So the cockpit layout, some of the things of importance here. We have the display units right here. We can actually see both the co-pilot and the pilot. We have the airspeed indicator right here, artificial horizon, which is blank right here. There would be a heading down here if the yoke wasn't in the way, and there's an altimeter over here. We also have things like radar, other gauges. We also have the flight control panel up here, some of the electrical control panels up here, and last but not least, the carpeted seats for extra comfort. No cup holders though, not that I can see around here. So a quick outline of the events that happened in Swissair 111. The flight departed at around 00:18 hours or UTC time from JFK. And about an hour later, they detect an unusual odor in the cockpit, and they misdiagnose it as coming from the air conditioning unit. They then 4 minutes later request to divert to Boston for an emergency landing, and the air traffic services asked if they want to land in Halifax, which they agreed to do. And at 1:20, they discuss performing a fuel dump. And you can actually hear the conversation between the captains and the crew discussing if they should dump or not. Now, think about fuel dumping. Some aircraft are required to have systems to jettison fuel in case of emergency. It's pretty much highly pressurized. They pressurize a tank and then blow it out the back of the aircraft in a fine mist. Why they do this is because just as aircraft have a maximum takeoff weight, they also have a maximum landing weight. And if they exceed that maximum landing weight, you risk damage to the landing gear and the structure of the aircraft. So for aircraft where their maximum takeoff weight is larger than their maximum landing weight by a factor of more than 1.05, they're required by law to have some sort of system to jettison extra fuel so that they can land safely in case of an emergency. So at 1:21, ATS requests their gross weight. In the recording, they ask how much fuel and how many passengers do you have, and the captain just give an answer. We have 230 tons, and they provide a route to fuel dump at a certain location because you can't dump fuel anywhere, and they haven't declared an emergency yet. And then at 1:23, something happens to their autopilot, and they notify ATS that they're taking manual control, and that they need more space to get to a lower altitude before landing at Halifax. So they request clearance for lower altitude. A minute later, they declare an emergency and request immediate fuel dump. Then they declare a second emergency, and at 1:31 is when it was expected to be the impact. The impact time was judged based on eyewitnesses, as well as they took seismic data from geological centers and found where the approximate time was where the aircraft went down based on the last recording from the transponders and the cockpit voice recorders. And they found a spike in seismic data around this time, which they assumed to be from the crash, the acceleration from the crash is about 350 Gs. So that would have definitely been a spike on local seismic activity charts. Here's a map of the flight and the disaster. We first see the smoke in the cockpit around 1:10, which is an unusual odor, and then at 1:14 they give a pan-pan radio transmission. Pan-pan means it's not directed at any one individual target. It's kind of directed to anyone who's willing to listen to them. So it could have been Halifax, Moncton, Bangor. It could have been this Halifax Shearwater, Halifax International Air Traffic Control. It could have been another aircraft. And the air traffic controller picks up on that and reroutes them to Halifax. They descend, and you see smoke is more in the cockpit. And then around this time, they don't have the charts for landing at Halifax because the control display unit didn't actually have the data for landing there, so they needed to land using charts, which the flight attendant moved the pilot's bag to somewhere outside of the captain's reach, so they had to move it back, so they wasted a little bit of time doing that. And then eventually at around this time, they discussed fuel dumping and diverted themselves to 360, which is true north. And the pilot switches the cabin bus to off, and then the autopilot disconnects. They declare an emergency, and their systems start going south. They lose their communications and then their transponder and crash. If you want to see where they were, their diversion starts just about here when they see smoke in the cockpit. They're much closer to Halifax than they were to Boston. If they decided to divert back to Boston, there's no way they would have made it back. Even making it to Halifax would have been shaky. So if you want to hear some haunting voice recordings, they're not really that haunting, I suppose. I linked them here in the YouTube channel. We're going to listen to them. But in case you aren't interested in listening to them, I put some highlights in here. And if you are interested in listening to them, you can skip to these portions of the video to avoid any sort of idle, quiet time. I will warn you that at around 140, 141, there's a very loud beep. And if you're wearing headphones, I would suggest you turn your volume down. Right now we're loading up this video.
Rescue Center, Halifax, Collector Officer Biller.
We're going to skip straight to 140 or 150 where the recording starts.
Craft calling, say again.
Swissair 111 Heavy is declaring fan. We have smoke in the cockpit. Request immediate return towards convenient place, I guess, Moscow.
When he says Swissair 111 Heavy, the actual number of the aircraft started with an H, so that heavy means that it's the H aircraft, or aircraft number that starts with H.
Swissair 111 Center.
Swissair 111 Heavy, go ahead.
Would you prefer to go into Halifax?
Stand by. Bunker Virgin 12 will be standing by.
Virgin 12, roger, stand by.
Affirmative, Swissair 111 Heavy, we prefer Halifax from our position.
Swissair 111, roger, proceed direct to Halifax, descend now to flight level 290.
Level 290 to Halifax, Swissair 111 Heavy. Swissair 111 Heavy, off the mask on, go ahead with that. Okay, it's the 300 Zulu weather was 100 at 9 knots, 15 miles, scattered at 120, broken at 250, plus 17, plus 12, 2980.
111, can you tell me what your fuel on board is and the number of passengers?
Roger, stand by for this.
Having you contact the Moncton Center now, 119.2.
119.2 for the Swissair 111.
Roger.
Moncton Center, good evening. Swissair 111 Heavy, flight level 254, descending flight level 250, on course Halifax. We are flying at the time on track 050.
Swissair 111, good evening, descend to 3000, the altimeter is 2979.
We would prefer at the time around 8,000 feet, 2980 until the cabin is ready for the landing.
Swissair 111, you can descend to 3 and level off at intermediate altitude if you wish, just advise.
Roger, at the time we descend to 8,000 feet, we are anytime clear to 3,000, I keep you advised.
Okay, can I vector you to set up for runway 06 at Halifax?
Say again, latest wind, please.
Okay, active runway Halifax 06. Should I start you on a vector for 6?
Yes, vectors for 6 will be fine, Swissair 111 Heavy.
Swissair 111, roger, turn left heading of 030.
Left heading 030 for the Swissair 111.
Okay, it's a back course approach for runway 06, the localizer frequency 109.9. You've got 30 miles to fly to the threshold.
Fuel on board is 230 tons. We must dump some fuel. Maybe do that in this area during the sun.
Okay, I'm going to take you. Are you able to take a turn back to the south, or do you want to stay closer to the airport?
Stand by short, stand by short.
Swissair 111, Roger. Turn to the left heading of 200 degrees and advise me when you're ready to dump. It'll be about 10 miles before you're off the coast. You're still within about 25 miles of the airport.
Roger, we are turning left, and in that case we are descending at the time only to 10,000 feet to dump the fuel.
Okay, maintain 10,000. I'll advise you when you're over water. It'll be very shortly.
Roger. We see the emergency checklist for air conditioning smoke.
Swissair 111, say again, please.
Sorry, it was not for you, Swissair 111. It was internal. It was my fault. Sorry about.
Okay.
Did you catch how much fuel and how many people was it?
He said 230 tons. He's got to dump some fuel. I'll get back to you with an update on it. He's going to go down south. I'll take him out down off the coast a ways.
Swissair 111 at the time we must fly manually. Are we clear to fly between 11,000 and 9,000 feet?
Swissair 111, you can block between 5,000 and 12,000 if you wish.
Swissair 111, we are between 12 and 5,000 feet. We are declaring emergency now at time 0124.
Roger.
11 Heavy, we starting dump now. We have to land immediate.
Swissair 111, just a couple of miles. I'll be right with you.
Roger. And we are declaring emergency now, Swissair 111.
Copy that. Swissair 111, check you're cleared to start the fuel dump.
Hello?
Yeah, so that was the recording of the Swissair 111 in the last recordings from the recorder. And that last remark, some of the wizards in the YouTube comments, which I don't know if that's actually a reliable source of information for this, but they said that the last word that the pilot said was either Rolf, which is German for smoke, or Rolf, meaning up, like pulling up. But again, that's YouTube comment magic, so I don't know if that's actually too reliable. So investigation recovering the aircraft. Here's a picture of the heavy lift operations. You see a giant crane on a barge. It's used to uplift heavy pieces of aircraft from the water and take them back into shore. And they concentrated on this area of the cockpit from the nose to station 741. And inside here we can see kind of this galley right here being reconstructed. You see the inside of the cockpit, these doors, part of the lavatories. You can see that a lot of the frame is still intact, but a lot of the skin got taken clean off from impact with the water and from heat exposure. These heavy lift operations, like I said, it's using crane to lift pieces out of the water, and if they're too deep or too heavy to use with a skimmer or diver, then you use the heavy lift. And there's also a scallop drag, which they take a giant chain link net or rake, and they drag it along behind a vessel along the floor of the ocean. And they use together all the parts they can and haul them back up in the boat and take them back to shore. There's also remote vehicle operations, where remote operated vehicles are used to kind of scan the water with using sonar or laser to find pieces of aircraft or changes in the topography of the ocean to see where the aircraft might have hit. And the suction hopper dredge, a dredge is used to take sand or silt or whatever from the bottom of a waterbed and bring it up. So a vessel will have some sort of skimmer, and it'll take the sand up, load it into the boat, and pump it somewhere else. So it'll sift all the sand out, only leaving aircraft parts. And a quote from the investigation report, particular emphasis was placed on debris exhibiting heat damage, burn residue, or unusual markings, which we'll take a look at later. The areas of interest, this is just a diagram of the wiring above the cockpit, primarily from the in-flight entertainment system, which we'll talk about later, but you also have your ducts that carry air conditioning and wires. You have your avionics circuit breaker panel, some more bundles up here. Here's a zoomed up area of it. We also see what it looks like that's not in a colorful, pretty picture. You have these wire runs right here. We'll talk about these letters over here. We have the cockpit door, station 420, and these are the in-flight entertainment wires. You also have an insulation blanket, which is to protect that area and the cabin from heat and sound from the airplane. So before we talk about the actual systems and the crash a little bit more, we're going to talk about what the wires are in an aircraft. From the FAA Regulations and Policies Manual, a wire is a single solid conductor, shown here in this diagram, or a stranded conductor, shown here, covered in an insulating material, which is around here. If you have multiple insulated solid conductors or multiple insulated strands bound together, then you have a cable, not a wire. And the wires are built to, we have a military standard, a mil spec. You have mil spec right here, and then W for wire. And the old standard was this 5086A, A for aircraft, but now it's the 22579. They both have these same specs, but they changed the insulation, going from a PVC or a nylon insulation to an ethylene tetrafluoroethylene insulation, or ETFE. And here we can see a diagram of a strand. We have multiple conductors twisted together in a strand, and the wires are tin-coated copper, which are supposed to withstand 600 volts and temperatures up to 150 Celsius. And here's the coating, this extruded ETFE. Now, more things about aircraft wires. The conductor, most of them are either copper or aluminum. Copper is the one that's used more. It's more expensive, but it's more conductive, stronger, and easier to bend to whatever shape you want. Whereas aluminum is a little bit cheaper, it's lighter, and it has less discharge at high potential, meaning there's less possibility of potential being carried to other circuits. So there's less electrical interference there. Copper is still the more used one. Now, the wires have to be plated, or else they'll oxidize they'll oxidize. And oxidized metals are much, much less conductive. So the most common one is tin, which is the cheapest, it's easiest to work with, and it's readily available. Silver and nickel are a bit more expensive, and the benefits you get from using nickel or silver is you have higher temperature capacities before the wires start losing their conductive properties and they start changing. The insulations are normally polymers. The biggest concerns are resistance and dielectric strength. Resistance meaning a high resistance is less likely to have a current go through it, and dielectric strength means if you have a high dielectric strength, then that means between two conductors you won't have as high of a potential. So it's kind of like a capacitor. If you have a capacitor is two conductors with a dielectric in between it, and depending on the material of that dielectric, that will determine how high the potential is between those two. So you don't want a potential between the other wires. And other factors, resistance to physical harm, such as abrasion, cuts, and bending moments. Also thermal capacity and flame resistance, other things as well. Now, the insulator types, so you have this ETFE, which we saw on the previous slide. It's a polymer made from carbon, fluorine, and hydrogen bonded together like this. PTFE, which is a polytetrafluoroethylene, also known as Teflon is the trade name. It's just the carbon-fluorine polymer. And it's sandwiched around a layer of Kapton film, which is this lovely polymer right here. For those of you that don't speak chemistry, at the point of each hexagon is a carbon atom, and each of these are single bonds. The double lines are double bonds. So these are made of carbon, oxygen, and nitrogen. Or you have a sandwich of Teflon and polyimide polymer. And an imide structure is it's one of these. These R1s and R2s are placeholders for other molecules or even atoms, depending on what imide structure you want. Another factor is shielding. In your physics class, you learn that an electric current creates a magnetic field, And when you move that magnetic field around a conductor, you create a current. So so you need to have these wires shielded from each other, because if you have a lot of magnetic fields going around and those wires start moving in flight, then you will have interference between the two wires. So you need to have some sort of material that will shield them from each other so you have less interference and your instruments are more accurate. Now, specifically on the MD-11, we had this Douglas BXS 7007 and also the 7008. The biggest difference being the 07 was nickel coated and the 08 was tin coated, except at high gauges. And we also had different insulations and shieldings. So at the shieldings and insulations are actually different for different gauge length, for different gauge sizes. And the gauge size are determined by the AWG American Wire Gauge Standard, which is really easy to say that a wire is an 8 gauge rather than a wire is a 0.01475. I made that up. I don't know if that's actually true. But the actual relation between the diameter and the gauge number is shown here, where it's a decaying exponential depending on the gauge number in inches and both in millimeters. Now in this other slide, we saw these wire runs, and they're all labeled by letters. And these letters have a certain meaning. They're not just arbitrary names. They determine the location of the run, whether it's inside of a conduit, and what interference category it is, because you don't want radio interference interfering with your wires, and the actual name of the run. So, for example, our FDC run is a wire that runs in the cockpit drop ceiling, which is which is what the F code stands for, outside of a conduit, which is D. Where if it was inside of a conduit, then it would be V, W, Y, or Z, and it's the third in that group. It's the C run. Circuit breakers. Also, these little things are not the actual circuit breakers. They're many circuit breakers, and they make up a breaker panel or a distribution board. And these boards distribute power feed among its attached circuits and act as a protection against power surges. So they take all the power in and distribute it to all the other sources. The main ones we'll be dealing with in this emergency investigation is the overhead panel and the avionics panels. Now, the overhead panel draws power from the DC battery buses and the emergency buses, which if we go back to our power system, we have the emergency DC buses and the battery buses drawing power from these. We also have the upper avionics panel going from AC and DC buses 1 and 3 in the AC instrument buses. Meanwhile, lower avionics is drawing from DC bus 2 and DC ground bus. DC bus 2 is right here, and these are the other DC buses, and the DC ground bus is right here. We also have AC buses 1 and 3 for the upper and AC bus 2 for the lower. So the circuit breakers themselves, they're these little guys with this is the actual breaker. When the circuit breaks, this little button pops out, and when the pilot wants to reset the circuit, he just pushes it back in with his thumb. And these are all mounted up here. Now we have this lower avionics panel is taking power can convert. We have AC power from here and DC power from here. We see that the in-flight entertainment system, which we'll talk about a little bit later, has 4 breakers devoted to 15 amp AC power and 1 amp DC power. And here's the diagram of the in-flight entertainment network, which we'll talk about in a little bit. We have the main power supply cable down here. Here's where the avionics board is, and here's where the wires run above this cockpit drop ceiling area. Now, the IFEN, the in-flight entertainment network system, combines computer, video, and audio technologies to allow passengers to select movies, audio, games, news, gambling, and the moving map displayed through an interactive seat video display. This is from the aircraft investigation report. The IFEN consists of these 4 power supply units, which are all connected to each one of these circuit breakers. And what it needed is each power supply unit, its job was to convert the 115 volt AC power into a usable 48 volt power, kind of like the way you have adapters that take the 120 volt power from your house and convert it to a usable amount of voltage for use in appliances. AC bus 2 is the one that actually provided that power. Even though we have DC bus 2 for the lower avionics panel, this part of the lower avionics board takes power from AC bus 2. Now the 1 amp circuit breaker provided power to the relay, and the relay is what regulated the power from each of these units so they'd be balanced according to the power demands at the time. So that changed depending on how many people were actually using the in-flight entertainment system. Each of these use that 22579 spec wire. But the kicker is that these were all deemed non-essential equipment. And if that was to be malfunctioning, they were to be cut off by switching the cabin bus off. And which, if we look at the flight map, cabin bus was switched to off right about here at 1:23, about 8 minutes before the crash. But if we look at the circuit diagram, or the block diagram, AC bus 2 is right here, and the cabin bus switch is right here. When this gets cut off, you lose the ground service, the ground AC bus, and these AC buses right here, which are connected to other minor systems. When this is switched off. However, the IFEN was linked right here, so that means it wasn't cut off. So when there's a fault, it keeps faulting, even though they cut off the cabin bus. The only way to cut off this AC bus 2 would be to flip this switch, but even though it's wired in parallel, it would still be able to get power. You'd have to turn off this switch, take it away from the parallel network, and also to take it away from the generator. And that's bad. So looking at the wires from the in-flight entertainment network, these were all around station 383, which is where the cockpit door was. See, each of these are little arcing events, and these over here are areas where the tin coating was gone. And you can see right here, this picture matches this one right here. This is from the exhibit where there was some sort of electrical arc and the wire got fried. You can see that you have melted copper on the outside, no sign of any tin. And over on this wire, you can also see melted copper, and you also see corroded copper from the seafloor. Note that green color. You also see some melted copper up here. These are all on the scale of a few millimeters. And these are all wires from each of the 4 power supply units. Here's some more wires from the in-flight entertainment network. This is before the fire, a standard MD-11 in orientation. Here's where the copper melt was determined to be, and here's in reference to the overhead circuit breaker panel. Here's the actual bundle they recovered from the crash, and you can see that there's not a lot of insulation and coating left, but they used the remaining insulation to find out that all of these were from most of these were from the in-flight entertainment network power supply cables. And they actually found where the arcing signs were on these cables. You see that some of these have their tin coating still on, some of them still have their insulation, and most of them have it off, either from impact or from fire. So the fire damage, here we have the overhead as well as the avionics panels. The blue ranges from from 70 Fahrenheit to 650 Fahrenheit, which can either be just getting a little toasty from fire far away to from cold areas of the fire, which you can see kind of line up to these areas. These would be the least damage that were actually touched by fire. You see, these are kind of much less damage than the rest of the circuit breaker. And here we have kind of the same deal. The dark yellow goes up to 750 Fahrenheit, and the light yellow goes up to 1150 Fahrenheit. As you can see, these are the most damaged areas. Now the orange is signs of melt, which we can kind of see over here. Here we have some melted area, and then the gray is soot. You can see we have the soot going along diagonally along the circuit breaker. We have soot going along here. There are also marked circuit breakers, and these circuit breakers are all logged in the flight data recorder. And each circuit breaker, when it fails, there's actually a parameter linked to the flight data recorder on what goes away when that's turned off. So here we have the autopilot going away, then the yaw damper going away, and a flight control computer going away. We have another aircraft computer, an air computer going away, We have the electronics going away, electronic display for the display going away. We lose radio frequency transceivers, display units, another more control system failures, and eventually that 125 you see failure of the flight data recorder itself. And from quoting the flight investigation report, the fire spread and intensified rapidly to the extent that it degraded aircraft systems and the cockpit environment and ultimately led to loss of control of the aircraft. Now looking at fire damage, as we see actually a heat diagram of the cockpit area. We see the hottest areas right here about in this drop ceiling area about temperatures that go in from the 800s to 1,000 Fahrenheit. We also see another layout of the drop ceiling area with the in-flight entertainment wires. Also the avionics panels. Now this was protected with the MPET covered insulation blanket. MPET meaning metallized polyethylene terephthalate. Sorry if I pronounced that incorrectly. Which is designed to protect the cabin from thermal and acoustic. So make sure the cabin stay at the right temperature and make sure that the noise from the aircraft doesn't really get into the cabin. And it was shown that the blanket ignited as a result of exposure to electrical arcing, which those sparks can get up to 500 degrees Celsius, which is quite hot, and hot enough to melt the copper and the tin. Now, when the accident investigators investigated this, they took the material and tested for flammability by exposing it to these short-term sparks. And they got sporadic ignitions. Sometimes it would ignite on the first try. Sometimes it wouldn't ignite at all. Sometimes it took multiple sparks. But each time they did spark it, the circuit breaker would trip, and the current would stop flowing through the wire. So it would only be one spark anyways. So on the actual accident aircraft, the sparks did not trip the circuit breaker, so they continued to fault and cause more fires along that blanket. And how they actually test the flammability of certain materials, not in the investigation, but for certification, for materials in the cabin, they're tested with what's called a vertical Bunsen burner test. And here in these diagrams, you have the burner down here and a stand for the material in here. They need a specimen of 12 inches must be tested, but if there's no space on the aircraft that has a 12-inch specimen, or if it's impossible to find a 12-inch specimen, they can use a shorter one. And depending on the CFR requirements, it'll be exposed to either a 12 or 60-second ignition from the Bunsen burner. Ignition time means time exposed to the flame of the Bunsen burner. And the three things they're testing for is flame time, which is how long the material continues to stay aflame after turning off the Bunsen burner, and that cannot exceed 15 seconds or else the material fails. There's also drip flame time. During the test, material might collapse off of the specimen and onto the ground of the testing chamber. And if that happens, then it cannot stay on fire for more than 3 seconds or 5 seconds depending on the test. And if it does, the material fails. And burn length, that measures the length of the original specimen that exhibits any sort of burn damage, so charring, melting, or flames. It cannot burn for more than 6 inches or 8 inches depending on the length of the test. Now, wires are tested a little bit differently. They're tested with a 60-degree Bunsen burner test. And they tauten a wire up over a 24-inch length and at a 60-degree angle, and a Bunsen burner is oriented perpendicular to it. And the flame is positioned 1 inch from the wire, and the wire is exposed to either a 30-second or a 60-second test, depending on the CFR requirements. And there's 3 criteria here. There's extinguish time, which is kind of like the flame time, except it's for wires. The flame must be extinguished in 30 seconds or less after the flame is removed after the Bunsen burner is turned off. And also the drip extinguish time, which is kind of like the drip flame time. If any material collapses from the test stand, it cannot burn for more than 3 seconds. And the specimen length of burn damage on the specimen cannot exceed more than 3 inches or it fails. However, the wire does not have to be intact during the entire test. It is allowed to break. So breaking of the wire does not necessarily constitute a failed test. So let's take a look at tying it all together. Pretty much an overview. How did everything go wrong here? So first we had failure of the power supply units. Some sort of electrical fault in it caused a spark to come from an electrical arc. So it could have been a defective wire, it could have been a defective power supply. But in the report it says they don't know what led to the initial arcing event. But it did happen above the cockpit. But that spark ignited the insulation blanket, which was made of flammable material which caused fire to propagate. Also, the fact that the caps for the air conditioning units were made of flammable materials. Conditioned air was being put back into that cockpit drop ceiling area, giving more fuel for the fire. The pilots didn't also catch the fires in the entertainment network originally. They thought it was the air conditioner, and to be honest, a wisp of smoke isn't really grounds for diverting the aircraft. It could have just been a one-off thing. Something might have overheated and tripped a breaker, and now it's better. So they misdiagnosed it, but they didn't really have any way to properly diagnose it. They just kind of took a guess. Also, the circuit breakers were unable to handle thermal and electrical loads from arcing. So when you have an electrical arc, that's a lot of voltage and current going across it. So the circuit breaker would either trip and cut off power to electrical systems, or it would fail and cause those and still conduct the current through it and cause those systems to just break. The pilots were also fooled by, and this also leads into the pilots being fooled by a failure of the fire alert system for the engines. So engine 2 there was a display that engine 2 was on fire, even though engine 2 wasn't actually on fire. So the pilot put it out by turning off engine 2. And when the crash investigators looked at the engines, they saw that damage was done to the engine 2 that was consistent with it not being powered. Also, there were no regulations that required fire detecting or suppression methods in that above cockpit area because, well, it wasn't really planned on having fire there. And there also didn't have any active in-flight firefighting measures, so in the cabin there would be a fire extinguisher, but in any of those areas where it would be hard to reach, there wasn't any active fire suppression. So fire would be able to spread with it, and there was not much you could do about it other than make an emergency landing and get everyone off the plane. Now there are, in the accident investigation report, in one of the appendices, an emergency plan for if there is smoke and which systems to power down and try to isolate in the event of emergency, and then plans to divert. Also, and ultimately, the fire-stable displays and inhibited cockpit accessibility, which is a euphemistic term for the cockpit was on fire, impeding the pilot's spatial orientation. It was at night and they lost all their navigation, and ultimately led to destruction of the cockpit and loss of control of the aircraft. Also in the investigation, they ran through all possible scenarios in which it would be possible to land that aircraft. So if we go back to the flight map, they started it from right here when the pilot said there is smoke in the cockpit, we are diverting. If they would have made a beeline for Halifax, started descending immediately, and done everything right, like had the charts within reach, turned off the proper electrical systems. The report stated that they might have been able to make it to Halifax, but so many systems would have been damaged by the fire that would have been impossible to make a safe landing. So they probably would have been able to make a crash landing at Halifax. However, it would not have been by any means a safe landing because of loss of the autopilot and destruction of cockpit systems and the controls. So the report stated that it is evident that even if the pilots had attempted a minimum time emergency diversion starting at 1:14:18, it would have been impossible for the pilots to continue maintaining control of the aircraft for the amount of time necessary to reach the airport and complete a safe landing. So how do we react to this? The FAA started introducing some airworthiness directives specific to the DC-10 and to the MD-11, which included taking away all those flammable blankets, revoking all the approval for the type certifications of those IFEN systems, which means any system that is similar to that one is not allowed to be installed in the aircraft. And any insulation blankets consisting of a similar one similar material to the MPET must be replaced with materials that pass flammability test. And there are also a few other ones that were more blanket, no pun intended, for other aircraft, which is removal from these flammable blankets, removal or deactivation of those entertainment systems that cannot be isolated in the event of an emergency. So they could actually get those systems approved if they could show that the entertainment network systems could be starved of power in the event of smoke. And also they needed to, airlines must be able to train crew and have manuals on board the aircraft that instruct on how to shut off that power to non-essential systems. However, so I told you this story, but there is also another story. So if you want to put on your tinfoil hats right now and get a little dose of some other truths, there was an article on the Canadian Broadcasting Corporation's website where in 2011, a former RCMP investigator claimed that the fire aboard Swissair 111 was not the result of an accident involving the electrical system, but actually a terrorist attack involving some sort of fire-based weapon. And his reasoning was that you had high-profile officials, such as a Saudi prince and a UN envoy who was negotiating peace relations between two African nations, and a relative of a former Shah. You had paintings and over $1 billion in jewels. And his reasoning was that in the damaged areas of the cockpit, there were levels of magnesium that were 10 times higher than to be expected, which magnesium isn't really too big of a component of aircraft structure or systems, but there's also magnesium in the seawater, so there would be traces of it that would be available in the crash investigation. And he also claimed that the heat levels that were recorded would be too high for a conventional fire. So his assumption is that when you have heat above 800 or 900 Fahrenheit, that's not really standard fire temperatures. That is the result of a magnesium-based fire weapon. So the TSB report is actually updated in 2012 to say that the Royal Canadian Mounted Police found no evidence to support the involvement of any explosive or incendiary device or other criminal act in the initiation of the in-flight fire. So rest assured, you can take off your tinfoil hat and hopefully trust the RCMP. So the sources I use for this, mostly I use the TSB investigation report for this flight, can be found at this link. A few FAA handbooks, the Aviation Maintenance Technician Handbook and the Materials Fire Test Handbook. Also the FAA website for those airworthiness directives. Also our course textbook, Aircraft Systems, Mechanical, Electrical, and Avionics Subsystems Integration by Moore and Seabridge. The awcwire.com is a trade website devoted to aircraft wiring, and a few Wikipedia articles for some other tidbits. So that's it. If you have any questions or comments, they're more than welcome. Please contact me, Carson Haack, at either cthack@crimson.ua.edu, or if you're a local student, you can see me in my office at M12 Hardaway Hall. I will say that if you would like to add anything to this presentation or make any corrections, they're more than welcome. When I started working on this presentation, I knew next to nothing about aircraft systems, in relation to power systems and electrical wiring, and I learned a lot writing this presentation. So if you would like to educate me a little bit more and help me expand that knowledge, I would be more than happy to accept that. Thank you so much for listening to this presentation, and have a good day.